Okay, so there are two ways that you can think of the kinetic molecular theory. You can think of the simple, straightforward way that you guys know and love, where the motion of the molecules basically determines what type of phase it's in, solid, liquid, or gas. Or now we can look at it in terms of gases. So when we talk about the kinetic molecular theory in gases, we're focused on an ideal gas. If it's an ideal gas, it's going to follow all of these rules. So the first rule is gases are made of small particles. Duh, they're really small. These gas particles are so small compared to the gaps between them that we can ignore the volume of the individual particles. That makes our calculations much, much easier. Okay, so because they're so tiny compared to the gaps between them, the spaces between them, we can ignore the volume of the gas molecules. Number three, the gas particles are in constant random motion. They move in a straight line at a constant speed until they bump into something else. They hit things that are in the container and they hit the sides of the container. When they hit something, specifically that's not another gas molecule, that's what forms pressure. Mostly we're concerned about pressure on the sides of the container, so that's what we usually talk about. For you, however, sitting in this gas that you're in right now, you are considered part of the container, so you have air pressure based on the molecules hitting you, how fast they're hitting you, how often they're hitting you. And the simple equation for pressure is just force per unit area, and that's it. The fourth rule is that gas particles are they don't attract or repel each other. There are no intermolecular forces between them. So when they get closer to each other, they don't push away because they're repelling each other, or they don't suck into each other because they're attracting. So there are no IMFs. And what this does is it helps it follow along the line in that when they do hit each other, there's no loss of energy. So they are considered to have perfectly elastic collisions. So if you're in physics, you know that you have collisions that can be elastic or not. Most collisions are going to lose energy. Yeah, they're inelastic. They're going to lose energy in that process. If you hit a tree, you're going to lose some of the energy as sound, some of the energy as motion to the front of the car crumpling up. Some of the energy is going to be changed or converted into physically harming the tree. So you have that loss of energy. In an ideal gas, you don't have this loss of energy. So you have a gas that's in a container, and you leave it there long enough, and if the collisions were not perfectly elastic, at some point the molecules would completely stop moving, and that would be they freeze, they change into a solid, right? And that doesn't happen. It just flat out doesn't happen. So our theory is that these are going to be perfectly elastic collisions, so we don't lose any of that energy. Number 5 on the ideal gases with the kinetic molecular theory is that the average kinetic energy of the gas is proportional to the Kelvin temperature. So the average kinetic energy of the gas is proportional to the Kelvin temperature. Okay, that's hugely important. And the reason we say Kelvin has no negative numbers. That's the big reason. And remember, we talk about temperature as a part of dealing with gases, and it's perfectly reasonable to have 5 degrees below zero, so negative 5 degrees in Celsius or even in Fahrenheit, and that would totally screw up all our calculations. So you can't have a negative volume, can you? Does that even make sense to have a negative volume? It doesn't. So what happens is they're saying, look, we need a temperature scale that has no negative numbers, and so that's why we have to use Kelvin. So when you're working with these gases, change your temperatures to Kelvin. There are some things that we deal with in AP Chem where you have to have it in Kelvin. There are some where you have to have it in Celsius. It just depends on what you're working with. So pay attention to what you're working with. Pay attention to the units of measurement that are in the problems that they give you on the AP test. Remember that Kelvin is equal to the Celsius temperature plus 273. So if you have negative 273 Celsius, it pops up to zero Celsius. Let me say that again. If you have negative 273 Celsius, you have 0 Kelvin, right? No negative numbers there. Okay, the last thing on here is that when we deal with ideal gases here, ideal gases follow all 5 rules. I'm going to say rules. We could say tenets or something like that, but they follow all 5 rules here. Ideal gases are most ideal at low pressure and high temperature. They're going to ask you that questions. Which gas is most ideal? They're most ideal at low pressure and high temperature. And again, that makes sense. Low pressure means they're spread out. High temperature means they're moving really fast. So, at low pressure, the volume of the molecules can be ignored because they're small compared to the total volume of the gas. So again, why is it that it has to be that they're most ideal at low pressure? Because that means they're farther apart. The farther apart they are, the more gaps there are between the molecules, the easier it is to ignore the individual volumes of the molecules. They become, again, insignificant. Again, like that, add 1 foot to your 50 miles to Amarillo, and it's insignificant in the overall scheme of things. And then why is it at high temperature? High temperature, it's at high temperatures the molecules are traveling so fast that if there were any IMFs, they are insignificant. Okay, that's why low pressure and high temperature. Because we know that molecules have IMS. We know that they're polar. We know they have some IMS, intermolecular forces, attractions between molecules. We know they're there. It's just that when you have it at a high temperature, they are moving so fast, it's like, that's going to be insignificant. It's like you driving in a car and you've got your hand out the window and you're going to try and grab hands with someone as you go by. If you're going so slow in your car and the person on the side of the road has their hand out, you could probably do that, right? The faster you go, the more difficult it is to grab hands, yes, as you go by. And that's basically what we're talking about here. You're traveling so fast that they touch for such a short, tiny amount of time. They're going so fast that it's insignificant if there's an attraction between them because it's not going to take hold. Same way with repelling, it's insignificant in that sense. So they might ask you to justify, well, why is it that this is most ideal at low pressure or high temperature?